Hello everyone, I welcome you all for the third session of the chapter Wave Optics. In the previous session, we had learned about the theory of interference. There, we learned that if we have the two coherent sources of light, S1 and S2, which are emitting the light, and suppose if this is a wave emitted by the source S1 and this is a wave which is emitted by the source S2, and if these two waves are going to interfere at point P, due to the constructive interference, what happens to point P? The light energy is going to have a more brightness here, which is because of the constructive interference. And if these two waves interfere destructively, then at this point the light energy will be having a lesser brightness, or even we can call that as a darkness. So this is what we have learned from the previous class. Now in this class, what we have to learn is, we have to understand the phenomenon of interference through the experimental setup which was done by a scientist called Thomas Young. Let us understand it. The experiment is called Young's double slit experiment. So in this Young's double slit experiment, we have a source here. So this source is emitting the monochromatic light, and here we have two slits which are nothing but a small pinholes. Okay, so S1 and S2 are the two small pinholes. So these two sources, these two pinholes are equidistant from this S. Okay, the source is nothing but a source which is emitting the monochromatic light, and S1 and S2 are the two small pinholes which are equidistant from this source. Therefore, S1 and S2 are emitting waves here, and this S1 and S2 are nothing but the coherent sources. Okay, this S1 and S2 becomes a coherent sources. We know that from the interference phenomenon, when the two light waves are emitting from the coherent sources, if they are superimposed on each other, then it forms a interference fringes. Remember the definition of interference? Interference is the modification in the distribution of light energy due to the superimposition of two or more waves which are emitting from the coherent sources. The same thing is happening here also. S is a source which is emitting the monochromatic light, and S1 and S2 are the two small pinholes which are acting as a coherent sources, and the light waves from these two coherent sources are going to interfere on the screen to form interference fringes. So what are those interference fringes? How does the interference fringes looks like in this screen? If you say this is a screen S, if you say this is a screen, and on this screen they are forming a pattern of light energy, how does this looks like? See, this is how the fringe pattern looks like. So if S1 and S2 are emitting the light, and at this point, let me say at the center, due to the interference of light from the two sources, at this point, due to the constructive interference, it is forming a bright fringe, and to the next it forms a dark fringe. A dark fringe is formed because of the destructive interference. The light waves from the source S1 and S2 are somewhere meeting at this point, say, and at this point it is forming a dark fringe. This dark fringe is due to the destructive interference. So the pattern of light energy will looks like this. It forms a alternative dark and bright fringes. This is nothing but a phenomenon. This is because of the phenomenon of interference. The bright fringes are formed due to the constructive interference, and the dark fringes are formed due to the destructive interference. So at the center, always it forms a bright fringe. Okay, this is how the pattern of interference looks like. Now we need to derive an expression for the fringe width. So what do you mean by a fringe width? What is the width of this line? Okay, this is called as a bright fringe. So we said that this is a bright fringe. So what is the width of this fringe? So we need to derive an expression for this fringe width now. Now let us represent the experimental setup of Young's double slit experiment schematically. So how does it looks like? This is a source. The distance between the two sources, the distance between the two slits is written as small d, and the distance between the slits to the screen. So screen is nothing but where the interference fringes are formed. So this is nothing but capital D. Now, and here let us draw the two lines like this, and at the center, so at this point center O, it forms a bright fringe because of the constructive interference, because from S1 and S2 this point is at equidistant. Therefore, at this point it always forms a bright fringe due to the constructive interference. Next, say from this point to somewhere here, the point is P, which is at a distance of x from O. Okay, so there is a point P here, and at the point P, and this point P is at a distance of x from this O. Next, imagine the light waves from the source S1 and S2 are reaching the point P like this. Okay, these are the two light waves which are falling at the point P to form a fringe. So at the point P, what is the condition for obtaining the bright fringe and a dark fringe? That we need to derive, and also we need to derive the expression for the fringe width here. So I have already explained you that. So on the screen it is forming a alternative dark and bright fringes like this. The fringe pattern is just look like this. Well, this is how the fringe pattern looks like. So at the point P, what is the condition for obtaining the bright fringe and dark fringe? That we need to derive now. Say this point is some Q and this point is some R. Okay. Now if you observe, the distance between the two slits is D, and this distance is equal to D by 2, correct? So this distance must be equal to D by 2, and also this distance is also D by 2, correct? So if this is D, then this will be half of that, D by 2 and D by 2. Now we need to look at the two right angle triangles here, S1PQ and S2PR. So those are the two right angle triangles. So from right angled triangles S1PQ, from that right angle triangle S1PQ, S1P square should be equal to S1Q square plus PQ square, correct? Let us write this. S1P square is equal to S1Q square plus PQ square, correct? Next, S1P square is equal to, if you observe the diagram, from S1 to Q, the distance is nothing but the capital D, which is nothing but the distance between the slits to the screen. So this S1Q is equal to D square plus, what about PQ? PQ is nothing but OP minus OQ, correct? But OQ is taken as D by 2, therefore OP is X and OQ is D by 2. Therefore this length PQ should be equal to X minus of D by 2. Therefore let us write this PQ as X minus D by 2, and we have whole square. Let us write as it is. Call this as equation number 1. Next, similarly we have one more right angle triangle S2PQ, S2PR, correct? S2PR. So from this right angle triangle S2P square is equal to S2R square plus PR square. Let us write this. S2P square is equal to S2R square plus PR square. This is PR square. This is equal to, again S2R is equal to D only, correct? S2R is equal to D. Therefore this S2R is D, therefore this will be D square plus PR square. PR is nothing but PO plus OR, correct? PO plus OR. PO is taken as X and OR is nothing but D by 2. Therefore this will be x plus d by 2 the whole square. Okay. Next, take this as equation number 2. Now we need to derive an expression for the condition to obtain the bright fringe or a dark fringe here. So for that, let us subtract these two equations, equation 2 and equation 1. Subtracting equation 2 and 1. Subtracting equation 2 and equation 1. So what you will get is, first let us subtract the left hand side of the equations. Therefore S2p square minus S1p square equals, the right hand side of the equations are d square plus x plus d by 2 the whole square minus d square plus x plus d by 2 the whole square minus of d square plus x minus d square plus x minus d by 2 the whole square. So we get that equation. So now let us do this again. S2p square minus S1p square. This is in the form of a square minus b square. Therefore this can be written as S2p plus S1p into S2p minus S1p. Correct? The LHS of this equation becomes, this is in the form of a square minus b square. Therefore this will be S2p plus S1p into S2p minus S1p. And this will be equal to, so here d square can be cancelled with d square, and let us expand this x plus d by 2 the whole square. So x plus d by 2 the whole square expansion will give us x square plus d square by 4 plus 2 into x into d by 2. Correct? And here we have minus, let us write this minus. Here x minus d by 2 the whole square. So if I expand this one, what you will get is x square plus d square by 4 minus of 2x into d by 2. Now what are the things you can cancel here? X square and this minus x square gets cancelled, d square by 4 and this d square by 4 gets cancelled, and this term remains 2x into d by 2 minus of minus plus again 2x into d by 2. These two gets cancelled, these two gets cancelled. xd plus xd will be 2xd. Correct? xd plus xd will be 2xd. Next. Now in the left hand side we have this S2p plus S1p into S2p minus S1p, which is equal to 2x into d. Now take this S2p plus S1p to the denominator. Therefore this will be S2p minus S1p is equal to 2xd divided by S2p plus S1p. Now let us assume a condition that this x, the value of x, and this value of d, the distance between the two slits. So these values are very much lesser than the capital D. So this is about 1.2 meter actually, and these are in the order of millimeters. That is why the distances x and d are negligible when compared to the capital D. So by assuming this condition, keep LHS as it is, S2p minus S1p, which is equal to 2x into d divided by S2p plus S1p, which means this point P is very much close to this O. That is why the distance S1p and S2p is almost equal to the capital D. Therefore, if these two are equal to D means we will get D plus D here. Therefore, 2xd divided by 2d and cancel these two. Therefore, we obtain S2p minus S1p is equal to x into d divided by capital D. But this S2p minus S1p is nothing but the path difference between the two waves. Okay. S2p minus S1p gives us the path difference between the two waves. Therefore, the path difference that is equal to delta x, which is equal to x into d divided by capital D. Now we need to write the condition for obtaining the bright fringe and dark fringe. Let us write this. See, for bright fringe, the path difference delta x should be equal to n lambda, correct? The integral multiples of lambda. So for this condition we obtain a bright fringe. Therefore substitute the value of path difference is equal to xd by d by that equation. Therefore say this is equation number 3. Therefore equation 3 becomes for this condition. So instead of delta x I will write n lambda. Therefore n lambda is equal to x into d divided by d, where this x is written as xn, which means the position of the nth fringe, the position of the nth bright fringe. Therefore xn is equal to take this d towards this and this d towards the denominator. So we get n lambda into capital D divided by d. This expression is the position of nth bright fringe. This is the position of nth bright fringe. If we have the values like n lambda d by d, where n is equal to 1, 2, 3, 4, 5, etc. So if I substitute the value of that n as 1, 2, 3, 4, 5 for the integral multiples of lambda d by d, we obtain the bright fringes like this. So to obtain the bright fringes at the distance x, what is the condition? The condition is like this. We have to get the integral multiples of lambda d by d. There we obtain the bright fringes. Then how do you obtain the dark fringes? What is the condition for dark fringe? The path difference is equal to 2n plus 1 lambda by 2. The odd multiples of lambda by 2. For that we get a dark fringes. Let us write that. To obtain the dark fringes, the path difference is equal to 2n plus 1 lambda by 2. Therefore, substitute the value of delta x in the equation 3. What we obtain is 2n plus 1 into lambda by 2 is equal to x into d divided by d. Therefore, the position of some nth dark fringe is xn is equal to. So, we are writing for the position of the nth dark fringe. Xn is equal to, take this d towards this, therefore this will be 2n plus 1 into lambda into d divided by 2d. So this is the position of the nth dark fringe. So xn is equal to 2n plus 1 into lambda d by 2d. So this is the condition for obtaining the dark fringe. Okay. So the position of the nth dark fringe. So the values of n are 0, 1, 2, 3, 4, 5, which means if I get the odd multiples of lambda d by d, for the odd multiples of lambda d by d, we obtain the position of the nth dark fringe. So in this fringe pattern, to obtain the dark fringe, what is the condition? What is the distance x? The distance x should be equal to 2n plus 1 into lambda d by 2d. Next, we need to obtain the expression for fringe width. What is fringe width? A fringe width is the distance between the any two dark fringes or any two bright fringes. Okay. A fringe width is the distance between the any two consecutive dark fringes or consecutive bright fringes. So this is a fringe pattern. If I say this is bright fringe and this is a bright fringe, the distance between the two consecutive bright fringes can be called as a fringe width, or the distance between the two consecutive dark fringes is nothing but a fringe width. So all the fringes are equally spaced and all are having a same width in the interference pattern. Now if I want the width of one fringe, one bright fringe, how do you do that? The distance between the two consecutive dark fringes or bright fringes will give us the fringe width. Let us obtain the value of fringe width now. So fringe width is represented using the symbol beta. So fringe width is the distance between. So how do you obtain this beta? Beta is equal to xn plus 1 minus of xn. So if I substitute the position of the n plus 1th fringe and position of nth fringe, we obtain the fringe width. Therefore, the fringe width is written as, we know that the position of the bright fringe is given by this equation. So, using this expression, we will obtain the fringe width. So, the position of the n plus 1th bright fringe minus position of the nth fringe. So, let us do this. Xn plus 1. Substitute n as n plus 1 there. Therefore, this will be n plus 1 into lambda d by d minus xn is this only. This is n into lambda d by d. Therefore, if I subtract these two, what you will get is, this is n plus 1 minus n. N plus 1 minus n is nothing but 1. Therefore, 1 into lambda d by d. This is the expression for the fringe width in a interference pattern. So, this derivation will be asked for 5 marks in your examination. So, obtain the expression for the fringe width in Young's double slit experiment. What are these lambda d and d? Lambda is the wavelength of light used. This capital D is the distance between the slit to the screen, and small d is nothing but the distance between the two slits. So, this is the expression we got. So, this expression is the expression for the fringe width. Well, in this session, we learnt about the Young's double slit experiment, and in the next session, we will be meeting with another concept. Until then, thank you.